Hello, I'm Thandatron. In this presentation, I would like to share our recent work, Fairness Continual Learning Approach to Semantic Scene Understanding in Open-World Environments. This is a research study in collaboration between the University of Arkansas, Carnegie Mellon University, and MBZUF. This research has been sponsored by NSF DART Project and Google Research. The goal of continual semantic segmentation is to learn the segmentation model in the dynamic environments. In particular, it aims to learn new classes of the new data, while maintaining the information that has been learned from the previous classes. Then, under these learning scenarios, there are 3 challenges that have been identified. First, the catastrophic forgetting problem indicates the forgetting issue of the model about the previous knowledge, when learning on new training data. Second, the background shift problem refers to the classes of previous, or future data, that have collapsed into a background class. Third, the fairness issue refers to the problem of the model, where it behaves unfairly between classes in the data set, due to the class distribution. While the first 2 problems have been well studied in the prior work, the fairness problem, a major challenge, have not been well addressed yet. In continual learning, the class distribution of the semantic segmentation are often imbalanced between classes. For example, several classes tend to occupy the larger portion on the image, or exist more frequently than other classes. Therefore, because of this imbalanced problem, the model tends to produce prediction bias toward the major classes. To address the fairness problem, we introduce a novel fairness continual learning approach to continual semantic segmentation. In particular, first, we define the fairness metric for continual semantic segmentation. Second, based on the fairness metric, we propose a novel fairness continual learning approach by introducing a new fairness loss based on the class distribution. Then, to improve the consistency of the segmentation predictions, we introduce a new conditional structural consistency loss. Third, to address the problems of catastrophic forgetting and background shift, we introduce a novel prototypical contrastive clustering loss. In addition, we also prove our proposed clustering approach as a new, generalized continual learning paradigm of knowledge distillation. Our experimental results have shown the effectiveness of our proposed approach in fairness improvement on different continual learning settings. In our approach, our fairness objective in continual semantic segmentation aims to minimize the difference of error rates among classes, so that the model is able to fairly behave among classes. Then, we can further prove that fairness objective has been imposed by the continual learning objective. However, because of the imbalanced class data distribution, this imbalance has influenced the continual learning loss, and therefore, this results in the gradients produced in the majority group, largely dominant the ones in the minority group. Then, to address the problem of imbalanced data distribution, we reformulate our learning objective under the viewpoint of the ideal data distribution, where the learned model will behave fairly among classes. Then, we derive our learning objective into 3 major terms. First, the continual learning objective aims to address the catastrophic forgetting and background shift problems. Second, the fairness objective maintains the fair predictions produced by the model. This objective penalizes the prediction of classes, forcing the model to behave fairly based on the class distribution. Third, the conditional structural consistency objective enhances the structural consistency of the prediction. Then, our fairness continual learning framework can be summarized as follows. Given an image, we predict the corresponding segmentation maps. Then, the cross-entropy loss with labels of current learning task is imposed to the prediction, in addition with the fairness objective and the conditional structural consistency objective. In addition, the feature representation of predictions are further used to compute the continual learning objective. In our approach, we define the continual learning objective as the prototypical contrastive clustering loss, where features of the same class would be pulled closer, while features of different classes would be pushed far away. In addition, the deep representations of unknown classes will be grouped into the same cluster of unknown classes, to produce discriminative features against other classes. Let's take a look on our results. We deploy our model in the context of off-road segmentation and compared with the approach without continual learning.